do with our singular value decomposition with the formula A is equal to U sigma and then V transpose. So we already have our sigma term, and then with our two vectors V1 and V2, we can establish our V matrix, which is just putting them together in correspondence of the eigenvalues of the singular values that we have in sigma to make sure they all line up. And then in order to get V transpose, you would just transpose RV as seen here. Next, we're going to want to find our A times V1 terms and our A times V2 terms. So when we do A times V1, we get it's 3 by 2 multiplied by 2 by 1, so we get a 3 by 1 resulting matrix, which is negative square root 10, 2 root 10, and 2 root 10. And then we do the exact same thing with A, V2. But in this case, we get zeros for all of them. So the only way that we only have A, V1 having like actual values. And in order to double check that those two matrices are right for AV1 and AV2, you can take uh the length of uh those matrices. So you basically just take both all those terms, add them up, and we get for our singular value 1, or sigma 1, we have 3 root 10, and that's the same answer that we had from the beginning of the problem. And then for all the zeros, and those up, we get zeros, which is our singular term for 2. So we can only really work with our AV1 resulting matrix. Here we have U1 is equal to 1 over that singular value times AV1. And once we do that, we get negative 1/3, 2/3, and 2/3. And since that's the only one we have to work with, and we need our U to be a 3 by 3, we're going to extend this set of U1 to be an orthonormal basis in the R3, based on like the equation that you can make from that matrix or that matrix, which in this case it's negative x1 plus 2x2 plus 2x3 is equal to 0. When you do that, we have our u term already, our u1 term. For u2, you can set x equal to, or x1 to 2, x2 to negative 1, and x3 to 2, and that all sums up to 0. So there you know that's an orthonormal basis. And then also for U3, we do the same thing with different numbers that all sum up to 0, where x1 is 2, x2 is 2, and x3 is negative 1. And then therefore we have the U that was already given to us in the problem. This just verifies that that was the correct solution. And then when you put the entire thing together, where A is equal to U sigma V transpose, you have our U that we just solved for, the sigma with the singular values, and then the V transpose that we solved for a little bit ago in the question. And that is the singular value decomposition of that matrix. Very similarly, we're going to find the singular value decomposition of another matrix A, which in this case is all ones and zeros. And we were given a hint in this problem that one column of U can be 1 over root 6, negative 2 over root 6, and 1 over root 6. So I'm going to go through this problem a little bit quicker because it's the exact same steps, just with different numbers. So first we have A transpose A, which is a 2 by 3, 3 by 2. So the real thing is a 2 by 2 matrix. We're going to take the determinant to find the eigenvalues. When we multiply that all out, we get our eigenvalues to be 2 and 3. For our eigenvalue 2, we get our V1 term to be having x1 free and x2 is equal to 0. So I'm going to set x1 to 1, and then therefore x2 is still going to be 0. When we normalize that, it's going to be 1 over the square root of 1 squared, which is 1 over 1. So it's our exact same V1 as before we normalized it. It just already is normalized. We do the exact same thing with our lambda equals 3. We get x1 to be 0 and x2 to be free. So we have 0, 1 as our 2 by 1 matrix for V2. Normalizing this again is 1 over the square root of 1 squared, which is 1. So V2 stays the same as well. When we put those together into our bigger V, we have 1, 0, 0, 1. Transpose of that is the exact same thing because it is a diagonal matrix with all zeros. So when you transpose it, it's going to be the exact same. And to find our sigma, we're going to want to find the singular values from our eigenvalues, which is just the square root of all the eigenvalues. So we take the square root of 2 and the square root of 3, and we make sure they're lined up with their corresponding eigenvectors in our V to make sure that the singular value decomposition works throughout. Next, similar to the last problem, we're going to do our AV1 and AV2. When we do AV1, it's a 3 by 2 multiplied by a 2 by 1, so we get a 3 by 1 result for both of them. We get 1, 0, -1, and 1, 1, 1. Once again, we double check that our sigma 1 and sigma 2 are equal to our like the singular values, which is the length of the AV1 and AV2, which is just that means you're taking the square root of 1 squared plus 0 squared plus -1 squared, which is square root of 2, and the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. So those all check out. So those are all correct. Next, we're going to find our U1 and U2 this time because we don't have a 0 eigenvalue or it's a 0 singular value. So we're going to do U1 is just 1 over the singular value times the AV1 that we found. So we have 1 over root 2, 0, -1 over root 2. And we do the same thing for our U2, which is 1 over root 3 this time, times the AV2, which is 1, 1, 1, to get 1 over root 3, 1 over root 3, and 1 over root 3. Next, we need a U3 term. So we need to have a projection of these two U's in order to get our U3 term that fits the problem. And when we do that, it comes out that they're all zeros. So we get a 3 by 1 matrix of all zeros. So then therefore, it was also given into the problem at the beginning that one of the columns of U can be 1 over root 6, -2 over root 6, and 1 over root 6. And when you do the length of that, you also it all works out, the math all works out. So that's going to be our U3 term of this matrix. So putting the U together, you're going to have the U1, our U2, and our U3 all put together. Then you're going to have our sigma, which starts with our eigenvalue of lambda is equal to 2 in the same size matrix as our A. And then we're going to have our V transpose term also corresponding to our sigma term. And then once you do that, we have our singular value decomposition of our second matrix in the form A is equal to U sigma V transpose as seen on the screen. Thank you.